So all along we've been working with the dot product, and you'll remember before that if we took the dot product of two vectors, so let's say that we have the vector v and we dot it with the vector x, and we know that if the result of that is 0, that v and x have to be perpendicular to each other, or if they're sitting in 3 or more dimensions, so if they're sitting in R3 space or R4 space, etc., we have to call them orthogonal. But orthogonal and perpendicular have the same idea. V and x are orthogonal to each other if their dot product is 0. So we know that, but now what we want to do is kind of expand this idea past just two single vectors. All we have here is we just take two individual vectors and say they're orthogonal to each other if their dot product is 0. We really want to be able to talk about this now in terms of subspaces. We want to be able to take an entire subspace and say whether or not it is orthogonal to a whole different subspace of vectors. So let's say that instead of just these two single vectors, v and x, let's say that we have a subspace defined by this vector set, so we'll call it capital V, and it's made of a bunch of vectors. So we'll just say v1, v2, v3, and so on, all the way up to Vn. And then let's say that we have some other vector set, and we won't say what it's called yet, but we have some other vector set, and it is full of x vectors. So we have x1, we have x2, x3, and so on, all the way up to some final x vector. And I'm going to say xm because we don't necessarily have to have the same number of vectors in each set. So I didn't want to say xn and give you the idea that we have to have the same number of vectors across the two sets. So we have some number of vectors in this set, some number of vectors in this set. They might be the same number of vectors, a different number of vectors, but the point is we've got two vector sets here. And we're going to assume that V is a subspace, meaning it's closed under addition and closed under scalar multiplication. What we say is that if every single vector v is orthogonal or perpendicular to every single vector x, and of course that would be the same then the opposite way, every single vector x is orthogonal to every single vector v. If that's the case, then this vector set x we can call v perp or v perpendicular. We have this little kind of upside down capital T, and that little symbol is the perpendicular symbol, so we call this v perpendicular or v perp. And we say that v perp is called the orthogonal complement of v. We could also say that v is the orthogonal complement of v perp. These two are orthogonal complements of each other. And if they are orthogonal complements of each other, again, that means that every vector in the one set is orthogonal to every other vector in the other set. So v1 is orthogonal to x1, and it's orthogonal to x2, and it's orthogonal to x3, etc. v2 is orthogonal to x1 and x2 and x3. v3 is orthogonal to all these x vectors, and x1 is orthogonal to v1 and orthogonal to v2 and orthogonal to v3, etc. x2 is orthogonal to v1 and v2 and v3. So you get the idea. Every vector in v is orthogonal to every vector in v perp and vice versa. That, of course, means that I could take the dot product of any vector from the set v and any vector from the set v perp, and the dot product of those two individual vectors would be 0. So another way that we can express v perp, we sometimes say that it is all the vectors, again we'll stick with x, all the vectors in Rn space, assuming that v is defined in Rn space, and that's something we should say too. V and v perp will always exist in the same space. So if v is defined in Rn, then v perp is defined in Rn as well. We can't have v perp defined in 4-dimensional space and say that these 4-dimensional vectors are all orthogonal to maybe these 2-dimensional vectors if v is defined in R2. They have to be defined in the same space so that we can have that orthogonality make sense. So let's say they're both defined in Rn, then v perp, so we'll say v perp, is any x in Rn where the dot product of any generic x with any generic v from our sets up here is equal to 0. Again, back to that idea of orthogonality. from the dot product, and we say that for every vector v, which is in the vector set v. So we define v_perp that way as well. And we also want to say that assuming the vector set v is a subspace, if v is a subspace, we know automatically that v_perp is a subspace, and we can prove it to ourselves by showing that v_perp is closed under addition and closed under scalar multiplication. So if it's going to be closed under addition, we already know we can take two vectors in v_perp, and we can say that the vector x1 dotted with some vector v, we know that's going to be equal to 0. We know that the vector x2 dotted with the same vector v is also going to be equal to 0. Again, going back to the idea of orthogonal complements. If we then add these two equations together, we get x1 dotted with v plus x2 dotted with v is equal to 0 plus 0, or just 0. We know from properties of dot products that the dot product is distributive, so we can rewrite this left-hand side as x1 plus x2 dotted with v is equal to 0. And this right here is what shows us that v_perp is closed under addition, because we said that x1 and x2 are in v_perp. Well, if it's closed under addition, then that means that x1 plus x2 also has to be in v_perp. And here this equation is showing us that the vector x1 plus x2 dotted with a vector v is going to be 0, which means that x1 plus x2, that single vector, is orthogonal to the vector v, which means that vector itself is going to be part of the set v_perp. So if x1 and x2 are part of v_perp, then x1 plus x2 is automatically part of v_perp as well. So it's closed under addition. And then same thing with being closed under multiplication. If we know x1 is in v_perp, then we would need to show that multiplying x1 by a scalar gives us a vector that is also in v_perp. So we would say some scalar times x1 dotted with the vector v. We're hoping that that's equal to 0. And again, by properties of dot products here, we can just use this associative property, pull the scalar out, and say x1 dotted with the vector v is equal to 0. Well, we already know that x1 dotted with v is 0 because these two are orthogonal to each other, which means their dot product is 0. So we get c times 0 equals 0, or 0 equals 0. So because that checks out, that means that over here we wrote a true equation, that cx1 dotted with v is equal to 0. So that means cx1 is orthogonal to v, which means it is part of the set v_perp. So we've proven that v_perp is also closed under scalar multiplication. So given that v itself is a subspace, we know that v_perp will always be a subspace as well. So now that we understand the idea of v_perp, the orthogonal complement of v, and its properties, let's look at an example to see how we would actually find v_perp if we're given v. So let's say we're given v as the subspace, which will be the span of, we'll do a two-dimensional plane in R3. So let's say it's spanned by the vectors 1, 0, 2, and we'll say -1, 1, and 3. So if this is our subspace v, then that means that v_perp, if we want to define it technically, has to be the set of vectors. So we'll say all the vectors x that are in, and they're going to have to be in R3 because v is defined in R3. So these are going to be the vectors in R3 where the vector x is always orthogonal to both of these vectors. So it's orthogonal to 1, 0, 2, which means x dotted with that vector is going to be equal to 0. And we know that x dotted with -1, 1, 3, so -1, 1, 3 is going to be equal to 0 as well. So those dot products are going to be 0 if we're defining the orthogonal complement of v. So then if we know that x is in R3, then the vector x is going to be given by three components, x1, x2, x3, which means that we can think about dotting this vector with the vector 1, 0, 2, And that dot product really is just going to be x1 times 1 plus x2 times 0 plus x3 times 2. So we can actually build out this equation. So we can say 1x1 plus 0x2 plus 2x3 is equal to 0. We can do the same thing over here. We'll get negative 1x1 plus 1x2 plus 3x3 is equal to 0. And now we realize we can actually put this into a matrix. So here we'll have 1, negative 1, the coefficients on x1, 0, 1, 2, 3, and we have this augmented with the 0 vector. To put this into reduced row echelon form, we can add the first and second rows to replace the second row. So we'll keep the first row, 1, 0, 2, and then 0. And here for the second row, we'll say negative 1 plus 1 is 0, 1 plus 0 is 1, 3 plus 2 is 5, and 0 plus 0 is 0. Now we have this in reduced row echelon form, and we can pull back out a system of equations. So when we pull a system back out, we'll get x1 plus 2x3 equals 0, and we'll get x2 plus 5x3 equals 0. And then we want to solve this system for the pivot variables. The pivot variables, of course, are coming from the first two columns because those are the columns where we have pivot entries. This is a free column. So we could think about this as the pivot variables are x1 and x2. The free variable is x3. So if we solve this system for our pivot variables, that means we're solving it for x1 and x2. So we can say x1 is equal to negative 2x3, and we can say x2 is equal to negative 5x3. So then if we come up with this solution here for x1, x2, x3, we set that equal to our only free variable, x3, and then we need a column vector here. We know x1 is equal to negative 2x3, x2 is equal to negative 5x3, and x3, of course, is just equal to 1x3, so we get a 1 there. What this tells us then is that the orthogonal complement v perp is given by the span of this single column vector. So we could say v perp is the span of this column vector negative 2, negative 5, 1. And based on that, if we think about this geometrically, v was given to us as the span of two three-dimensional vectors. So really, the subspace v is a plane in R3. V perp, the subspace v perp, is given as the span of one single vector, which means it's a line. So the span of this single vector represents a line in three-dimensional space, which is perpendicular or orthogonal to the plane given by the span of these two vectors in R3 space. And geometrically, that makes sense as well. If we think about R3 space, so let's just really quickly here say that we have R3 space, which looks something like this. So we have R3 space. If V is given as a plane, so let's just say that that plane looks something like this. So we have this plane, this is V. You might think that V perp is another plane that is orthogonal to this plane. But in fact, that can't be true, because if we try to think about some orthogonal planes, this is kind of hard to draw, but let's say it looks something like this. We have, maybe it comes like this, and then like this, and then we sort of have this where it cuts across the plane, and then down below the plane, something like that. You might think that those planes can be orthogonal, and they can kind of sit at a 90-degree angle to each other, but where they intersect one another, so if we think about some vector here, which is sitting at the intersection of the two planes, like this vector is common to both planes. It sits in the yellow plane, and it also sits in the blue plane, which means that that vector is contained in both sets. It's contained in V and V perp, but it can't be orthogonal to itself. So because of that, it just doesn't even make sense to have a plane that could be orthogonal to a plane. That's why instead we have this line here as the line that's orthogonal to the plane, because the line could be maybe something like this, and then it hits the plane, and then below the plane, something like that. But this line could be orthogonal to the plane, and they don't have any vector in common that sort of blows up the relationship, the orthogonal relationship between V and V perp. So given a subspace V, that is how you go about finding its orthogonal complement, V perp.